So what about periodic orbits? In this particular context, I like to use the term introduced by my colleague Rich Carswell and call them recurrent, because that's what you experience when you look at three-dimensional flow. What you see is you see some turbulent motion, then you see a shape you have seen before in the flow. Some pattern state, coherent state, whatever. But mathematically, this is just a periodic orbit, except it's in infinite dimensional state space, because these things have infinite dimensional state space. So the main thing about periodic orbits, it's possible to find them. I will discuss a little bit how you find them, but you can actually now, you have tools to find them, at least in Kuramoto-Shivashinsky. You need more demanding tools, but they're available on our website. If you want to deal with Navier-Stokes and do it at home, you can do it at home. You download channelflow.org to study fluids turbulent and set in motion by contour-moving planes that shear them. That's called plane Couette flow. Or you can use openchannel.org code, which enables you to simulate fluids moving down pipes. What happens in those cases is that they're time-dependent, so periodic orbits, when you compute one, might look something like that. And it will do things that dynamical systems do. If I put equal time ticks, I might slow down and spend lots of time here, and then might speed up and go crazy and do something violent and come back and slow down. If you compute the time average of that object and compute, for example, dissipation on it as 1 over 1 period of periodic or relative periodic orbit, you take your solution, your flame front, and you take two spatial derivatives of it, square it, and compute it at an instant in time over the space. That's time dependent. That's very easy to compute if you have solution, if you have periodic orbit. I put and remove as much energy. This is average of this, time average of this is 0. So I'll find that mean of every periodic orbit is someplace on diagonal as well. Another question is, if I populate the turbulent sea, the ergodic trajectories, and now I have to remember, everything is happening in infinitely many dimensions, or in numerical computation, 100,000 dimensions. We're only looking at them in 2. It's just one projection of many, but it's a nice, it's physically motivated projection. I will find that average is someplace on diagonal, and the theory claims that as I add these averages, I should actually get a good estimate of long-time average of a turbulent flow. This has not been persuasively established in practice, but not because the theory is wrong, it's just that it's quite complicated to figure out geometry of turbulent flow and how to use dynamical zeta functions and spectral determinants for this set of problems. That's a research level problem. But it's supposed to produce this kind of prediction. So this is wonderful. This is a physical thing you can get from the system. This is also rather bad in many, many ways. So let me now be a Cassandra and say why this is stupid now that I've told you how wonderful it is.